Today, we will be presenting on lambda calculus and its equivalence to the Turing machine. Lambda calculus is a mathematical notation which allows you to apply function operations to a particular set of parameters to receive an output. The principles underlying lambda calculus are instrumental to theoretical computer science in that they provide the conceptual basis for the modern programming language as well as other important concepts like functional programming, polymorphism, and recursion. It consists of three basic rules or features which characterize the calculus. First, you have variables. These are simply symbols which represent something like a mathematical or Boolean value. Variables can either be free or bound, which we explain shortly. Next, you have abstractions or functions. These act as operations which are applied to some set of parameter variables. Third, you have applications. Applications take abstractions and perform their operations on some given input to transform the values into something else. These operations are able to take place because of two fundamental concepts called different types of reductions, which lay the foundation for the other operations in lambda calculus by actually allowing functions to be performed on arguments. First, you have alpha reduction or alpha conversion. Alpha reduction simply allows a variable to be renamed to be another variable. This is important when you have increasingly complex function operations with many different variables on which operations will be done. Second, you have beta reduction. We will demonstrate beta reduction more formally later, but it is essentially the principle which allows for the substitution of an argument for the parameter variable in an abstracted function. Another property of variables in lambda calculus is that they can either be free or bound. If they are bound, they are preceded by a lambda term. Bound variables are tied to a particular function or abstraction, whereas a free variable is not. In layman's terms, bound variables denote what you might think of as the arguments to a function, whereas the free variables denote where variables are in a function body. When we say then that lambda calculus is equivalent in computing power to a Turing machine, we mean that it can compute or represent the same set of languages. This can be seen in the lambda calculus's ability to compute and perform any function on the set of natural numbers as pictured here, and as we will also show in this example.
The lambda calculus is equivalent to the Turing machine, and thus should be able to emulate any possible Turing machine. We can take a simple machine, for example, the Turing machine that increments any input by 1. As we can see, the input here is 4, and the Turing machine stays in the start state until the head moves to the end of the input, and then it changes the first 0 it sees to a 1 and goes to the accepting state. The result is that the tape now contains the binary representation of 5. I will show that it is possible to replicate this with the lambda calculus. The lambda calculus is always in the form of functions followed by a function body. The lambda symbol represents a function and any variable next to it is bound to it, while variables past the dot are part of that function's body. Inside of the calculus, you can actually define any arbitrary data type, including the natural numbers in addition to 0. The standard approach to doing this are the Peano axioms, which are a set of rules regarding natural numbers. It essentially says that every natural number a has a successor a plus 1, and that we can represent these successors as s of a using lambda calculus. Since s denotes the successor of a, we can represent the first two natural numbers as follows. Here, s denotes the successor of a, which is a plus 1. To represent the natural numbers in lambda calculus, we can simply take them in as arguments to a function. If we use z to represent a 0 and s to represent s, we can come up with a representation for 0. For shorthand, we will simplify 0 to be in the form on the right-hand side of the equation below. Now we see that 1, 2, and 3, and so on can also be represented using this same method. As you can see, 0 is itself, 1 is 0 passed into s, 2 is 0 passed into s twice, etc. This makes sense because 1 is 0 applied to the successor lambda s, 2 is 0 applied to two successors, etc. Using the same notion, we can define a successor function which increments any natural number representation that is passed into it. I use different variables to differentiate it from the natural number representations. W, y, and x correspond to a, z, and s, respectively. As you can see, it essentially applies one extra copy of s to a after assuring that a uses the same z and s. We can apply the successor function to any natural number representation, such as 4 from before. Once we have this form, we use a process called beta reduction to evaluate the lambda calculus. Beta reduction is simply a substitution method used to break down lambda functions into a state where no more reductions are possible. It is just the substitution of a bound variable in a function body with a function argument. In the first example shown below, for instance, the function argument lambda z u on the right-hand side replaces all occurrences of x, which is the bound variable on the left-hand side in the function body. Since there is only one occurrence, the lambda z.u gets substituted after the lambda y.y, and the reduction ends. If we repeat these steps using our successor function and the representation of 4 from before, we will eventually reduce down to the representation of 5, which shows that we can increment numbers using the lambda calculus. As you can see, the blue characters represent the bound variable that is to be substituted. The green characters are all occurrences of that bound variable in the function body, and the red is the input to be substituted into the bound variable's locations. So in the first step, you see the input of 4 is substituted into the successor function, and as it goes along at each step, it eventually comes to the end where the resulting is lambda sz dot, and then it is followed by 5 s's and then a z, which is the natural number representation of 5 according to the rules that I set earlier. So thus you can see that it is possible to do an increment using the lambda calculus. This is just one of many examples that shows the equivalence between the Turing machine and lambda calculus.
History about how the equivalence came to be discovered. The informal definition of an algorithm is a collection of simple instructions for carrying out some task. They've played a huge role in mathematics for a long time, but the notion of algorithm itself wasn't given a precise definition until the 20th century. In 1900, mathematician David Hilbert famously proposed 23 mathematical problems, the 10th one involving algorithms. With no formal definition of an algorithm, the 10th problem was to come up with, quote, a process according to which it can be determined by a finite number of operations. In this case, he was talking about a process to determine whether a polynomial has an integral root. Even though there was no formal definition yet, he clearly assumed that such an algorithm existed and it only needed to be found. Of course, we know that no such algorithm exists, but for mathematicians back then, it was virtually impossible for them to know that with only an intuitive concept of algorithm and no clear definition. In 1929 to 1932, Alonzo Church developed a notational system called the Lambda calculus to determine algorithms. It was a formal system for mathematical logic. In 1935, he argued that any function on the natural numbers that can be effectively computed can be computed with his lambda calculus. Then, in 1935, Alan Turing independently developed the Turing machine. He similarly argued that any function on the natural numbers can be computed using his machine, and proceeded to show that the two definitions were equivalent. This discovery of their equivalence is what eventually led to the Church-Turing thesis.
Now we move to related principles of the lambda calculus. The first is the Church-Turing thesis that was developed in 1936. This hypothesis concerns the nature of computable functions. A computable function is defined as one that can be calculated by a machine. A function is effectively calculable if it can be solved by intuitively effective means. When Church created lambda calculus, he defined that a function is called lambda computable if it can be represented by a term of the lambda calculus. At the same time, Turing was creating what we know today as the Turing machine. He defined a function to be Turing computable if a Turing machine can compute it. The Church-Turing thesis combines these to say that a function is lambda computable if and only if it is Turing computable and generally recursive. The thesis states that every effectively calculable function is a computable function. The second related principle to the lambda calculus is the Church-Rosser theorem, which was also established in 1936 and is related to beta reductions. When applying reduction rules to terms in lambda calculus, the order with which the reductions are chosen does not matter, and will ultimately arrive at the same result. In more specific language, if a term m can be reduced to terms n and p, there exists a fourth term q that can be reached from both results, regardless of additional reductions.